Okay, we begin number 3.
Next question. Somebody's got a next question, right? Well, let's check the whole viewers.
We do 38 on the same page.
Sure. Okay, so it's 398, number 38. Okay, so we want to find all integers such that x to the fourth minus ax squared minus 4 is reducible in q of x. So we want x to the fourth minus ax squared minus 4 reducible in q of x. So here are the ways that this can reduce, since it's degree 4. One is you can have degree 1 factor, or if you don't have a degree 1 factor, since it's degree 4, it would have to be degree 2 times degree 2. Now, a degree 1 factor corresponds to having a rational root, or in this case, having an integer root. So, I'll write this as f of x is x to the fourth minus ax squared minus 4. And what are the potential candidates to be rational roots? They would have to be the divisors of negative 4, right? So that would be plus or minus 1, plus or minus 2, plus or minus 4. So the only possible rational roots are plus or minus 1, plus or minus 2, plus or minus 4. And notice we get saved a little bit of work because since this is an even function, 1, 2, and 4 are going to give me the same answers. So how could 1 give me a root? Well, f of 1, according to this, is 1 minus a minus 4. And notice, if 1 was a root, that's going to tell me what a has to be. This tells me that a is equal to what? Negative 3. So, 1 is a root precisely if a is equal to negative 3, in which case this reduces because it would have a factor of x minus 1. Same thing with minus 1. The only way minus 1 is going to give you 0, since this is an even function, is for a to be negative 3. Let's move to 2. F of 2 is 16 minus 4a minus 4. And the only way 2 could be a root is if this is equal to 0. But the only way that can happen is if a is equal to, in this case, 3. And again, all of these arrows actually reverse. When a is equal to 3, this thing is equal to 0, meaning plugging in 2 gives you 0. Also plugging in negative 2. one is 4, and again, plus and minus 4 give you the same answer. Plug in 4, you get 4, 16, 64. This is 256 minus 16a minus 4 equals 0. And that tells you that a is equal to what? And I think the significant thing is not a whole number. Because notice, if a is an integer, this thing is divisible by 16, and this thing is divisible by 16, but this is not divisible by 16. So there's no way an integer a could make this whole thing equal to 0. Long story short, if you solve for a, it's going to be some number divided by 16, and it's not going to go in. So there are no values of a that make 4 or negative 4 a root. So the only ways that you will have degree 1 factors is if a is equal to plus or minus 3. Again, ab minus 3 makes plus or minus 1 a root. ab plus 3 makes plus or minus 2 a root. So that's when you get the degree 1 factors. So far, so good. I like these problems. Well, not surprisingly, that's probably why I went into algebra. So we've taken care of the only values of a that can give us degree 1 factors. Now we do the familiar Kinnan factor to degree 2. X squared plus ax plus b, x squared plus cx plus d. If we wanted to, we could get rid of b and d and split this into 3 cases. As you, maybe I counted wrong, let's see. You could have b being 1 and d being negative 4, or you could have b being negative 1 and d being plus 4, or you could have b being 2 and d being negative 2. So one route that you could take is you could split this into 3 possibilities and you shrink down to 2 variables. That's one approach you can take. Or you can take the approach of, I'm just going to do one big problem with 4 variables and hopefully it's easy. I'll try it this way. So this becomes x to the 4th. Again, with the benefit of hindsight, it might turn out that the other technique might have been quicker. So, first observation, notice in many of these problems there's no x cubed term. So that immediately tells us that a plus c is equal to 0. So c is negative a, meaning every time we see c, we can turn it into negative a. So we can replace c by negative a. That makes this go away. That turns this into negative a squared, and like it did before, this becomes a times d minus b times x. Sorry, this should have been written as b. So we've got 3 unknowns, a, b, and d, and 3 equations. Well, again, the nice thing is there's no x term, so that says a times d minus b is equal to 0. And that splits into 2 cases. If the product of these 2 integers is equal to 0, one or the other is equal to 0. So one possibility is that a is equal to 0. The second possibility is that a is not equal to 0, which forces b to be equal to d. So let's look at the two possibilities. Whether you're in possibility 1, where a is equal to 0, or possibility 2, a isn't 0, but therefore b equals d, this term has now gone away. So, let's solve these. If a is equal to 0, that says b plus d is equal to negative capital A, and b times d is equal to negative 4. This looks like there might be some work involved, so we'll come back to that. In the case that a is not equal to 0, and b is equal to d, that makes life a lot easier, because if b is equal to d, this says that b times d is equal to negative 4, but if bd is equal to negative 4, and b is equal to d, that says b squared is equal to negative 4, but there's no way that the square of an integer can be negative 4. So in other words, that can't happen. So far, so good. So, I think we've pretty much narrowed it on. Namely, b times d has to be negative 4. Okay, there aren't that many possibilities. And whatever b and d turn out to be, there aren't that many possibilities. Then we'll just figure out what a turned out to be. In other words, we want to figure out what values of a can allow us to solve for b and d. So let's see. One possibility here is b is 1 and d is negative 4. I ended up breaking into these cases anyway. Next case is that b is 2 and d is negative 2. Next case, b is negative 1 and d is 4. Now, you might say that there are more cases, but they're going to give you the same values of a. Here's what I mean. We took the case of 1 and negative 4 for b and d, and we took the cases of negative 1 and 4. As I basically taken the cases of you have a plus or minus 1 and plus or minus 4. What I haven't done is I haven't looked at the cases of 4 and negative 1 and negative 4 and plus 1. And the reason I didn't take those is because the way I'm going to solve for a is by plugging in for b plus d. And notice, okay. Here, b plus d is equal to what? Negative 3. So a is equal to what? 3, which in fact was nothing new. If I looked at the cases of negative 4 and 1, then b plus d again adds up to negative 3, and a turns out to be 3, which I already got. If I look at the cases of 4 and negative 1, they add up to 3. That makes a equal to negative 3, which was already covered before. And if I look at negative 4 and 1, then b plus d adds up to 3, which makes a equal to negative 3, which also got covered before. So I'm not getting anything new here. So it turns out, if for these cases, if I ended up getting degree 2 factors, then these degree 2 factors also split into degree 1 factors. The only thing I haven't considered yet is B is 2 and D is negative 2. Notice I could also consider, instead of 2 and negative 2, I could also consider negative 2 and 2. But since I'm only interested in what these values of B and D turn into B plus D, it doesn't matter which one I take, because in both cases B plus D turns out to be 0. And I've come up with one new value of A, namely 0, which actually isn't too terribly surprising, because if A was 0, this is x to the 4th minus 4, which, as one probably does in an algebra 2 class, is a difference of squares. It's x squared minus 2 times x squared plus 2. So, if A is equal to plus or minus 3, they're degree 1 factors. If A is equal to 0, there are degree 2 factors, but no degree 1 factors. Because again, if A is equal to 0, this is just x squared plus 2 times x squared minus 2. The fact that you're hitting me with the hard questions is actually a good sign. I mean, it's fun for me because they're interesting. But it probably means that you've gotten through the easier ones. This is a good sign. Because again, I think this is a good problem. I'm glad we're talking about it. Probably harder than something you'd see on the test because it's pretty long. Next question. And these are pretty high-level questions, which is a good sign because if this is the level of the question that you're at a week and a half before the test, you're in pretty good shape. Other questions? Well, one possibility is we could call it quits, or spend another second or so thinking about what are your questions. In other words, it's still early, you've come this far. If you have questions, I'm not going to throw you out, but if we're done. So just think about whether you have other questions. Hopefully you can see from like a question of these forms that being irreducible tends to be the more natural state for a polynomial, because like that x to the 4th minus ax squared minus 4, there are an infinite number of choices for a to make a polynomial, and of all the infinite number of integers that you could put in for a, only 3 of them made it reduce. So plus 3, minus 3, and 0 were choices for a that made this reduce. Any of the other infinite number of polynomials, any of the other infinite number of integers you could have put in for a would give you something reducible. So, you know, when you look at integers, as you look at bigger and bigger and bigger and bigger collection of integers, the percentage of them which are primes starts to shrink. But when we start looking at polynomials, at least over the rationals, the percentages of them which are reducible is pretty small. Now that's obviously not true of the reals, because for the reals, once you get beyond degree 2, everything reduces. And for the complexes, once you get beyond degree 1, everything reduces. But for the rationals, they like being irreducible. They like being irreducible. They just tend to be. So, yes.
I just got a general question.
Sure.
You'll mostly be available via email if we have
Oh, yes.
questions.
I mean, I'll also be in the office sometime during the week, but you're probably busy then. But yes, I'm certainly available by email if it's then more convenient to follow it up with a phone conversation, that's fine too. Other questions? Well, should we call it quits? Well, if this is a faculty meeting, this would be the time that the move for adjournment. Okay, well, thank you for coming. I'm always afraid that I'm going to lose these.